Good morning, future presidents. Today, we are continuing on our talk of our discussion of nuclear energy. So let's pick up where we left off last time. So last time we talked about nuclear structure and radioactive decay. We talked about the competing forces inside the nucleus, so the electromagnetic repulsion of the protons and the strong force between all the nucleons. Okay, and we discussed how that led to radioactive decay. So let's talk today about how that leads to both nuclear weapons and nuclear energy. So the first topic we need to discuss, or the one that's going to dominate our discussion today, is the topic of fission. Which is where we can split heavy nuclei apart to release energy. Good morning, class. Excellent. I hear a lot of talking out there, so I'm writing. All about fission, very important topic. Okay, so fission, splitting apart heavy nuclei to release energy. So let's do the premier example of this, which is uranium-235, okay, which is an important natural isotope of uranium. Okay. So uranium, natural uranium, so this is going to be important for our discussion today. So the uranium that we can mine out in the world is only 0.7%, so less than 1% uranium-235. And it is 99.3% uranium-238. Okay. So it's over 99% uranium-238, which is going to be important. It's the uranium-235 that is the primary isotope that we want to discuss in terms of fission and using it for energy and for weapons. So, but it's important to remember that natural uranium is less than 1% of that key isotope, uranium-235. So let's draw a nucleus. This is our uranium-235 nucleus. Okay. Remember, uranium has 92 protons. And so this nucleus has 143 neutrons. And its diameter is about 15 femtometers. Remember, a femtometer is 10 to the minus 15th meters, so it's a very small scale. So this is a relatively big, this is a very big nucleus, actually, uranium-235. Okay. Let's remember the strong force. The strong force, remember, is what's holding this together. It's attraction between the neutrons and the protons. The strong force acts over a limited range of only about 2 femtometers. Okay. So that is the distance that the strong force acts. And when you think about it, so this whole nucleus is about 15 femtometers. The strong force that's holding it together is only acting over a small portion of that. That's the range of the attractive force. Okay. So when you think about it, this is not that stable of a configuration, right? The nucleons, so the neutrons and protons, are very strongly attracted to their neighbors, right? Because the strong force acts over at 2 femtometers, so a very limited distance. But the nucleons on this side of the nucleus which are 15 femtometers from the ones on this side of the nucleus, are not feeling that strong force at all. So they are not particularly strongly attracted to each other. They're feeling the repulsive force. Right? So this nucleus is held together by all the neighbors locking themselves together with the strong force. But on the big scale, it's not that stable. So you can imagine if we could break this apart just a little bit, right? If we could just separate this nucleus in half a little bit with a little distance, then suddenly the repulsive force would take over, and this would release a huge amount of energy as that nucleus expands, as it repulses each other. It's just these nearest neighbors holding each other very tightly that's keeping it together, but it's not that stable of a configuration. Okay, so if we can break it apart a little bit, then the halves will repel each other, okay, and break this into smaller nuclei. So this releases, this is called fission, of course, the breaking apart of a heavy nucleus into smaller nuclei. And it releases approximately 1 million times the energy of chemical reactions. That's a huge factor. So if you wanted to get the same amount of energy out of burning oil or coal, you need 1 million times as much, okay, in order to get that amount of energy out of it. So, question is, how can we break apart this nucleus? Because the nucleus is stable, or it's relatively stable. So we need to somehow get energy in there in order to break that nucleus apart if we want to force this nucleus to fission. And the way we can get energy in there, into the nucleus, is we can send in a neutron. Okay, so we can send in a neutron that has some energy and let it interact with that nucleus. The reason we can't send in a proton, or it's not very practical to send in a proton, is because the protons are going to be repelled by that nucleus by electromagnetic force. So the protons don't want to get anywhere near that nucleus. Okay? They're getting pushed away from it from the electromagnetic force. Okay? So neutrons are neutral, so they don't feel any force as they're getting close to the nucleus. They're certainly not being repelled. So it's possible to send the neutron all the way into that nucleus, okay, and give it a little kick. Okay? And what we want to do is just give it enough kick so it breaks that nucleus apart just a little bit, and then the electrostatic repulsion is going to force it together, force it apart very quickly. Okay, so uranium-235 is a unique natural isotope in this regard because it will split apart with slow neutrons. Okay. A lot of heavy elements will break apart if we send in a very high energy neutron into there. So we give it a lot of energy. We smack it really hard and break it apart. Uranium-235 is unique. It is the only natural isotope that if we send in just a very slow neutron, so one that's not has a lot of kinetic energy, but it's just moseying along here, gets attracted to that, it will absorb it, and the fact that it's absorbed another nucleon makes it unstable enough that uranium-235 will fission. It'll break apart. Okay? And there's no other natural isotopes that will do that. There are man-made isotopes, plutonium-239, which we'll talk about by the end of class today. But uranium-235 is unique in this regard. So that means it's a very easy source of energy for us. Okay? And in fact, it prefers to absorb slow neutrons. Fast neutrons will hardly react with it. So we'll talk about that a little bit more. But let's look at this reaction, what happens when we send in a slow neutron and let it collide with the nucleus of a uranium-235 atom, then this will break apart. And it breaks apart in a very important way. Okay? So first off, it'll take that nucleus, and most of the nucleons will end up in one of two lighter nuclei. So each one of those has roughly half of the nucleons that were in the original nucleus. Okay? But there's an important secondary product here, which is that it also releases 2 or 3 free neutrons. Okay, and I'll talk about that in one more second. So we've got the lighter nuclei, we have some free neutrons, and then we've got the energy. Okay, and the energy is actually not separate. The energy is coming out as the kinetic energy of these products, the lighter nuclei and the neutrons. Okay? And this is the energy we access for nuclear energy, for nuclear reactors. Okay? So now why does it release these neutrons? Well, remember last time we talked about how the heavier the nuclei are, the more neutrons they have in the nucleus to make them stable. Right? So heavier nuclei have an excess of neutrons over lighter nuclei. Okay? So that means when this uranium-235 breaks apart into 2 lighter nuclei, there are extra neutrons there, okay? And those extra neutrons will escape. And those free neutrons, there's on average 2 to 3 that escape every time a uranium-235 fissions. Okay? So, and then of course there is the energy. Okay? And this is a useful number to know, which is 1 gram of uranium-235 is the same in terms of energy as 2.7 tons of coal. So there's a huge amount of energy locked up in uranium-235 nucleus, okay, which we can release by using sustained reactions in nuclear reactor. Okay, so important part here, we're sending in neutrons to break this apart. Okay? 1 neutron in breaks apart this nucleus, okay, producing lighter elements, but multiple neutrons come out. Okay? So if we've got a reactor or a weapon that we have a bunch of uranium-235 nuclei around, then these neutrons are suddenly available to repeat this reaction. Right? They are available to fission other uranium-235 nuclei in the environment. And that leads to the possibility of a chain reaction. Chain reaction can occur because the 235 uranium, or the uranium-235 fission releases 2 to 3 more neutrons, which suddenly are available to fission further nuclei. Okay, so if each one of those neutrons produced an additional 235 uranium fission, then we would have a growing series of fissions that are occurring. So if each one, let's say each one produced 2 neutrons, so those 2 neutrons went on to fission 2 more uranium uranium-235 nuclei. Then we have 4 neutrons, and then 8. Okay, and you can see that the amount of energy that's being released is growing very rapidly. Okay. So but that turns out to be actually pretty hard to do. So we're going to talk about that today, why it's hard to make each one of these neutrons go and fission another uranium-235 nucleus. Okay. So, and we can control this somewhat. If it's an uncontrolled chain reaction, then that will result in an explosion, which is the basis of nuclear weapons. And if it's controlled, then we can harness that energy and control the reaction rate. And that's the basis of a nuclear reactor. But the weapons and the reactors work under basically the same principle, that we're fissioning uranium-235, and that produces more neutrons. And the question is how we control those neutrons to control the reaction rate. So let's do our demo of a chain reaction here. Let's see, Wade, can you focus in on this box? So what we got here is a series of mouse traps. Each one of the mouse traps represents a uranium-235 nucleus, so they're set, which means they're storing energy. Each one of those mouse traps has 2 bouncy balls on it, which represents the 2 neutrons that are going to come flying out of that explosion once that energy is released. And I am the person controlling the nuclear reactor, so I'm going to send in my first neutron into the reactor to start this reaction. Okay, and let's see, hopefully this isn't a reactor, but let's see. This is armed. Okay. So when each one of these, where'd that come from? We have spare neutrons up here. 10-minute half-life, right? They decay away. Okay, so here's our neutron. So I'm going to send this in. So I'm going to induce a first reaction inside of our chamber here, hopefully. And the first one's going to release 2 neutrons, okay? And those are going to go on, hopefully, to spread this reaction throughout the chamber. So. We had a little bit of a failed reaction there. Oh, wait, I got another one. Where did it go? It rolled off. It went behind me? Ah, there it is. Oh, good. Okay, let me start that reaction again. We got most of them there, not quite all of them. Let me give it a little bit more energy. That's okay. Well, we have a little bit of number of nuclei there, but you get the idea. So 1 reaction spreads to 2, 2 spreads to 4, and it grows up. It grows pretty fast. So we have a limited number of nuclei here in our chambers. So okay. So very important question is, can we control that reaction? Because if we can control it, then we have access to a huge amount of energy through those reactions. Okay, so an uncontrolled chain reaction, is actually very difficult to create in nature. And there are several reasons why. Let me list those out. Okay, so the first reason that an uncontrolled reaction is actually hard to produce is because of the composition of natural uranium. is, so it's 99.3% uranium-238, okay, which is not a fissionable material. It's less than 1%, so 0.7% uranium-235, which is the fissionable material. Okay? But this 99.3% of the uranium that occurs naturally absorbs most of the neutrons that are produced. So most of those neutrons that are produced by fissioning the uranium-235 will naturally get absorbed in uranium-238 unless we play tricks in order to get them preferentially absorbed in the uranium-235, which we'll talk about in a few minutes. So, but that means it's hard. It's hard to actually produce a sustained chain reaction in uranium-238, okay? Unless we enrich the material. And by enriching the uranium, so we're going to talk about this more almost the rest of the class. By enriching uranium, we're increasing the percentage of uranium-235, which makes it more likely that the uranium, that the neutrons will get captured in the 235 uranium instead of uranium-238. Okay? So, the second reason is that the released neutrons travel very quickly. They are released with a lot of energy, and they travel really fast. Okay? But it turns out that uranium-235 fissions not when fast neutrons are hitting it, primarily, but when slow neutrons are hitting it. So in order to make the reaction sustained, we actually have to find a way to slow down these neutrons. Okay? So the fast neutrons do not fission the 235 uranium very well until they are slowed down. Okay. And one way to think about that is they might actually pass by the nucleus. Okay? They might even pass through the nucleus, but they do it so fast that there's not time for a reaction to occur. So they actually need to be preferentially slow, and they're just kind of sticking on there. Okay? And once they stick on there, it becomes unstable to fission. Okay? So in order to slow these, we require a material called a moderator, which we use in nuclear reactors. Okay? Moderator is an additional material that we include inside the near the fuel, the uranium-235, to slow the neutrons so that they are preferentially absorbed by uranium-235. Okay, so let's we'll come back to that in just a minute. So the fission rate, okay, can lead to a chain reaction, and there's a question whether it's controlled or uncontrolled. And we have terms that I just want to clarify for you guys what they mean. So okay, so there's the fission rate. So we've already said that on the average 2 to 3 neutrons are produced in each fission of a uranium-235. And those potentially might go on to create more fissions, but they don't need to, or they don't have to. It depends on the configuration. Okay? It depends on whether they're absorbed by other materials. So the fission rate, there's 3 classifications we have, which you've heard before. The first one is critical. So you've all heard in movies that the reactor core has gone critical. Okay? That sounds bad, but it's actually a good thing. Okay? Critical just means we're getting one additional fission superinduced fission. Okay, so that means that on average, for each one of these uranium-235 nuclei that is broken apart, one of these neutrons will go on to fission another uranium-235. Okay? So for each one, we get one additional one. That is a controlled reaction, and this is the state that reactors want to be operating in. Okay? They don't want an out-of-control reaction. They want one where for every 235 that gets fissioned, it produces one more. Okay? So a nice, steady release of energy. Okay? The two other terms related to that are supercritical Okay, when a reaction is supercritical, it means that more than one neutron goes on to fission another uranium-235. This is a growing reaction. Okay, and so if it's supercritical, that's what leads to an explosion, explosive. So, of course, this is what the reactions are engineered to be in nuclear weapons, because we want them to grow. And you want them to grow very quickly because you want them to basically release a lot of energy before the weapon actually explodes apart completely. Okay? And then the last is subcritical, where we have less than one neutron produces a fission for each one. So, of course, this is a dying reaction or decaying reaction. Okay. And this is, of course, what occurs in nuclear reactors when we shut them off. Right? They become subcritical and the reaction rate dies down. Okay, so we are going to talk about nuclear reactors in 1 second. And I'm feeling the need to quiz you guys. We haven't done this for a couple weeks. So let's have a little quiz. You guys have your quiz sheets? If you don't have a quiz sheet, raise your hand. Let's see, and Wei, can you turn on this to the projector for me? I'm on stage right. Oh, almost there. There we go. Okay, this should be on now, Wei, so. Does anybody not have a quiz slip? Raise your hand, high and proud. Okay, you got one. Okay, let's see. Is this one not working, Wei?
Yeah, not seeing it.
You want me? I'll switch to stage left. This is VGA1. Oh, you guys aren't getting out of it that easy. We've got ways. Oh. Yes. Okay. Question 1. I think I erased this from the board. Oh, great. Good. So, a uranium nucleus has 92 protons. How many neutrons does uranium-235 nucleus have? Math question. We didn't guarantee there was no math. How many neutrons does that nucleus have? Okay, let's go on to question number 2. What percentage of an atom's mass is in its nucleus? A, over 99.9%. B, over 90% but less than 99%. C, 50%. Or D, less than 1%. Okay, let's pass those to the ends of the aisles. Okay, by the way, if you did not get my message on B-Space, next Tuesday's lecture, we're going to talk about the Big Bang, but it's optional, so it will not be on the final, and there's no homework and no essays on it. No quizzes on Tuesday either. One of the few days I'll tell you that, so. Okay, so your book talks pretty extensively about nuclear weapons, so I'm not going to talk any more about those in class because, you know, they're just uncontrolled explosions. They're not that interesting, even though they're very important. I want to just talk more about nuclear reactors and how we actually control and can harness the energy from nuclear reactions. Okay. So just some numbers. Nuclear reactors currently produce about 14% of the world's electrical energy. So they are currently, of course, very important. In a few countries they are critical, but they're not the dominant source of energy, okay, but they could be. In the US, that is approximately 20% of our electrical energy usage comes from nuclear reactors. But we have, so 20% comes from 104 reactors across the country. But an interesting statistic, if you guys don't know it, is that all of these reactors were planned and before 1974, right, and built basically either before then or through the 70s. Okay? And the reason is that it has been very difficult since basically the 3 Mile Island accident in 1979 to get any nuclear reactors approved and built in the US. So we have quite a sizable number of reactors, but so far they have not been growing for decades. Okay? So by comparison, France gets 75% of its energy of its electrical energy from nuclear reactors. Japan gets 25%. China gets 2%, but China is also growing very rapidly in their nuclear reactor program, and that will double over the next decade. So they'll be up to 4% by the end of this decade. So, so nuclear reactor has not been growing in the US. In France, it's critical. It's 75% of the electrical energy. But whether it grows or not in the US, well, we'll have to see. So it actually was poised to come back and start growing pretty rapidly, but the Fukushima disaster might have put that on hold a little bit. Okay? I don't think that's going to stall things in China. They are so desperate for energy that they'll get it wherever they can, including building their nuclear reactor programs. So I think that's pretty much guaranteed that that's going to go forward in China. So there are certainly some advantages for nuclear energy. Okay, some of the advantages to nuclear energy are that there are no carbon emissions. So nuclear energy does not contribute to global warming, or at least not significantly. There is so let me write down advantages. There is a 100 to 1,000 year supply, depending on how efficiently we use the uranium-235 that is distributed in the world. Okay. And politically, it plays a role in energy security because, for example, the U.S. has significant amount of uranium deposits, and we have a lot of friendly neighbors that have uranium, and so this feeds into the energy security or energy independence political arguments. So if we could get our energy from perhaps more friendly countries, including ourselves. Okay. Disadvantages are that it's very expensive to build new reactors. Okay, the technology is a lot more demanding than, for example, natural gas power plants, which are pretty commonly being built these days, relatively cheap. It's very hard, we already discussed, to get new reactors approved these days, especially in the US. And so there is a natural bureaucratic impediment for doing that. There's, of course, safety issues for both the reactor and for the radioactive waste that it produces. And of course, this was really driven home this year with the Fukushima disaster in Japan, which we'll talk a little bit about. And regular reactors produce a very important isotope, plutonium-239, which turns out to be another source of fuel. So how long our supply of 235 uranium could last kind of depends on how well we use the byproducts, including plutonium-239. It's another fissionable material. But this is also potential bomb material. okay, which we'll come back to in a second. So there are clearly advantages and disadvantages, okay? And to tell you the truth, I go back and forth on whether I'm pro or against nuclear energy. So, but it's important to know what the consequences are and what the advantages are, okay, and what the supplies are. So it's clearly a huge supply of energy, which would not lead to any further global warming, but there are clearly safety issues that need to be dealt with, as well as security issues, okay, that go along with nuclear reactors. So let's talk about how a nuclear reactor works. There are several different types of nuclear reactors, and they, for the most part, have 4 key components. And the design of the reactors sort of depend on, there's differences, different components can be used for these. I mean, different types of materials can be used for these 4 components, but most reactors have these 4 basic components. So let's talk about what the 4 components are that make up the core of a nuclear reactor. 4 key components in the core. Okay, so the let me draw you a picture, and then we'll talk about these in detail. So, oh, wait. Let me say, I'm going to give you examples of these components. For a specific reactor type. And the reactor type we're going to be talking about is called a light water reactor. Which is considered to be among the safest of the nuclear reactor designs, and it's the one that's most common in the Western world. So unfortunately, it's also what 3 Mile Island was, and it's also what the Fukushima reactors were. Okay, so there are other types of reactors, which we'll talk about a little bit, but the primary examples I'm going to give you are the light water reactors, which are the most common used today. Okay, so the 4 key components. We have fuel, which is some form of uranium-235. We'll talk about that more in a second. The fuel produces fast neutrons. Okay. And remember, those fast neutrons, we already discussed this a little bit, are not very good at inducing further fissions in the uranium-235. They need to be slowed down. So there is, in all these reactor designs, some form of what we call a moderator. Okay? And the moderator just slows the neutrons. Okay, so coming out of the moderator, we will have slow neutrons. Okay. So that is the second key component. We need fuel. We need a moderator to slow the neutrons that are coming from the fission reactions. Okay. Then if that were all we had, then we wouldn't have much control. We would be creating reactions and then inducing them to continue more. So there is another component, which are called the control rods. Okay. And the control rods are a little different from the moderators. The moderators are materials that are designed just to slow neutrons. The control rods are materials that are designed to stop neutrons. And so when a neutron hits the control rod, it is very likely just to get absorbed. Okay, so that means it's not free to go on and produce any more reactions. Whereas the slow neutrons, so hopefully some of them, or if your operator, if it's running correctly, some of them will go into the control rods to stop the reaction, and some of them will go on to produce further fissions in the fuel. So we have fuel, we have a moderator that slows the neutrons, we have control rods that can control the reaction by by basically absorbing some of those neutrons. So the more it absorbs, it will stop the reaction. If it brings it subcritical, it will stop the reaction completely. Okay? And then those neutrons, depending on how the control rods are functioning, can go on to create further fissions and more neutrons, okay, that can go on in the reaction. So those are three components. And then the last component, which I'll just draw as surrounding this picture, is some form of coolant, okay, which removes the heat from the system. And that's the whole point. The coolant is what's carrying the energy out of this. Okay? It's also important for the reaction to keep this stuff in the core from getting hot. Okay? But it's that heat that it's pulling out of the core that goes on to produce power in the electrical power plants. So those are the 4 key components. Let's talk very briefly about what these are. So first one is the fuel. Okay, so for all the reactor types, it is some form of 235 uranium mixed with 238 uranium. Okay, so remember there is a natural composition of uranium, okay? But we can play with that composition in order to depending on the reactor type. Okay? So for light water reactors, so this is the type we're going to be talking about primarily. Let me give that the initials LWR so I don't have to keep writing it over. Okay? So light water reactors okay, the fuel is the uranium, but it must be enriched. Okay. And by enriched, we mean we have to change the composition. Remember, natural uranium is only 0.7% uranium-235 and is 99.3% uranium-238. Okay? For these reactor designs, that is too much uranium-238. It would absorb too many of the neutrons, so you can't create a sustained reaction in that. Okay, so the uranium has to be enriched. And by enriched, we need to adjust it so it's around 3% uranium-235, and that makes it about 97% uranium-238. Okay? And by enriching it, by increasing the fraction of uranium-235, you make it more likely that the neutrons that are produced in a fission reaction will go on to hit another uranium-235 instead of uranium-238. Okay, so not all reactor designs use enriched. Okay? There is a design called heavy water reactor, which you can read about in your book or on Google, which uses natural uranium, but it uses funky water, heavy water, which I don't want to talk about. But for a normal light water reactor, we need to use enriched uranium, which is a higher fraction. Now, turns out that creating enriched uranium is not that easy. We'll come back to that in 1 second. So let me continue on with the components, and then we'll come back to that. Okay, so that is the fuel for a light water reactor. The next component is a moderator. And a moderator is a material designed to slow but not stop the neutrons. Okay, so for a light water reactor, so let me repeat this. So it slows but does not stop the neutrons. So ideally, you don't want the moderator to stop the neutrons because then it's not actually helping you to produce more uranium-235 fissions. It's actually stopping you from producing more 235 fissions. So you want it just to slow the neutrons but not absorb it. In a light water reactor, the moderating material is actually the water itself. It's just normal water. Light water is just normal water. It's just water. Right? And this is a water reactor. Okay? So it turns out that water, or normal water, is not an ideal moderator because normal water does absorb slow neutrons. It absorbs it a little bit more than you might like. That turns out to be an advantage. It turns out to be a safety feature, which we'll come back to. But the fact that the moderator actually absorbs neutrons, okay, instead of just slowing them in a light water reactor, that's another reason that we have to enrich the uranium, okay, because we need to up the probability that a neutron hits a uranium-235 nucleus. Okay? So the fact that the water in the light water reactor is acting as a moderator, but it's not a perfect moderator, means that we have to have a little bit more push to get the reaction to continue. Okay, so next component are the control rods. Okay, these are materials that absorb slow neutrons. Okay, and the fact that they can absorb slow neutrons mean we can control the reaction rate by inserting or removing these rods. From the core. Okay, so here's a little model of what a nuclear core might look like. Okay, and here you can imagine that that these are all fuel rods, so they're just literally rods of fuel material, okay, that we stick in the core. In this design, the gray part is the moderator, it's the slowing, and these are control rods. And the idea is that if we have the control rods inside the core of the reactor, they are absorbing the neutrons, the slow neutrons, making the reaction rate subcritical so that it basically dies away. Okay? And then when we want to actually start the reactor up, we literally are removing these rods. Okay? And the further we remove them, the less neutrons are absorbed, which means the higher the reaction rate is. Okay? And ideally, when we are running a reactor, we are basically just controlling how far these rods are in the reactor, okay? And keeping that reaction rate critical so that we have a one-to-one reaction rate. So for every 235 uranium that fissions, we produce one more uranium-235. So that's literally how they control the reaction rate, by inserting these control rods in and out of the cores of the reactors. And there's a couple different materials that are very good at absorbing absorbing neutrons. Either boron or cadmium are especially good materials. So these light water reactors will have rods of this material literally stuck in the core that they can move in and out. Now, one safety feature that reactors have is that these control rods, you can imagine they are being pushed in by really heavy springs. So they're being always continuously forced into the reactor to turn it off. Okay? And if we want to actually start the reactor, we actually have to literally pull them up. Right? So we need to provide some sort of electric power or something to pull them out of the core. And if the electricity gets killed in the reactor for some reason, then the safety default is that those springs will automatically kick in. There's nothing pulling the control rods back out. The motors have died, and so they get pushed back in automatically. So that is one of the control features for nuclear reactors, is that the control rods should be forced in, right? And you actually have to literally pull them out in order to get a reaction to go. Okay, so the last piece of that is the coolant. Okay, and that's what transfers the heat out of the core. And that has two important functions, of course. One is to keep the core from overheating. That's a lot of energy you're producing in a very confined space. And the second, of course, is that heat is the whole purpose of having a reactor. You're sending that out to electric power generation, a separate plant that is located nearby, which uses that heat to produce electricity. Okay? And for a light water reactor, the coolant is the same as the moderator. It's the water. And this actually is the safety feature, the basic principle of safety behind light water reactors, which is if the core starts to overheat, then the water will evaporate out of the system. So that sounds really bad, having your coolant disappear, but you also, that means that the moderator disappears. So the water is doing the moderation. And so if the water disappears, then there's no moderator, which means that there's nothing to slow these neutrons. And so they no longer will produce fission. So the reactor automatically goes subcritical if the water in the core evaporates. So that is a natural safety feature for these light water reactors, which is why it's the most popular design that's used around the world today. So the original designs used separate material for the moderator. Most of them used graphite, which is a form of carbon. And the original reactors were designed with these graphite cores. And graphite is not as safe a design. In fact, Chernobyl in the Soviet Union was a graphite reactor when it blew. And so we'll talk about that in just one second. So let's talk about the three major nuclear accidents that we've had. So 3 Mile Island, Fukushima, and Chernobyl. Okay? So before I start talking about them, let me ask if there's any questions about this stuff. A lot of new ideas thrown at you guys today. Yes? Right, so your question's about Fukushima and what happened with the water there. I'll talk about that in 1 second. Yeah, that's a great question. So yeah, hopefully we'll make that clear in 1 second. Yes? Fast neutrons react much better with plutonium-239. So I'm hoping to get to that right after we get to talk about the disasters. So hopefully we'll come back to that in just a second. So the question was about the plutonium-239 that's produced in here. Yes? How do you enrich uranium? Great question, which we're going to come back to in 1 second. So you guys have really good questions. I shouldn't even ask if you had any questions. Let me push forward with through the accidents, and then we'll hopefully answer these questions, and then hopefully we'll have a couple minutes at the end if there are any more. Okay, so 3 accidents I want to talk about. 3 Mile Island, 1979, Fukushima in 2011, and then Chernobyl, which was in 1986. So turns out 3 Mile Island and Fukushima are actually very similar. So, so I'll talk about those together. So both of those reactors are light water reactor designs, which means that they have water which is acting as both the moderator and the coolant for the system. And both of them actually failed in a very similar way, but for very different reasons, which I want to talk about. So the one issue that all reactors have is that you can stop the fission reaction. Right? So we can use control rods to shut off the fission reaction. We can get rid of the moderator so that there's nothing slowing down the neutrons, which stops the reaction. But even if we stop the reaction, it doesn't mean the core of the reactor suddenly gets cold. In fact, it stays hot, and it stays hot for a long time. And the reason is because when you're creating the fissions inside the reactor, you're also producing a lot of radioactive nuclei inside the reactor. And when those decay, they release their energy. And so even when you shut the nuclear reactions off, there's a lot of energy that's being produced residually inside the reactor. It's not anywhere near as much as produced when the actual fission reaction is going, but you still have to keep it cooled. Otherwise, that heat will evaporate all the coolant, and it'll start melting the inside of the core. And that's what a meltdown is. Not when the reaction gets so high, the fission reaction gets so high that it doesn't have power, but it's when you shut it off and there's just the residual radioactivity that still requires you to cool down the core. Okay, so, and if it's not cooled down, it will melt down. So, 3 Mile Island and Fukushima are both examples of where the cooling system failed after the reactor was shut down. So these reactors were not running at the time. Okay, both of them had been shut down, but the core was still very hot from radioactive decays that had been produced while it was running. So in 3 Mile Island, the problem was actually, so you guys are a little young for this, but 3 Mile Island occurred in 1979. It was when a reactor on the East Coast melted down. And a parcel had a release of some radioactivity into the environment. So it was a very big effect, and has had a very lasting effect on the US nuclear policy. So that reactor was shut down, and that still means that the cooling system needed to be running, right? So it still needed to keep that core cold. And what happened with 3 Mile Island was that they had a valve that got stuck, and it almost sounds silly talking about it, but then in the control room, they had actually laid it out really poorly, so the controllers did not have a good idea of what was going on when this valve got stuck. And they ended up manually turning off the emergency cooling system because they actually thought that there was too much coolant in there. So it was completely one of these nightmare scenarios where the designers just designed a kind of a poor user interface, and they allowed the users, the control operators in the reaction room, to have the ability to shut off the cooling system, the emergency cooling system, which they did. Okay. And once they did that, then the core started to melt down and created a partial meltdown of 3 Mile Island. So you probably don't want your operators to be able to manually override your emergency cooling system, or at least have much stronger control over that. Now, Fukushima, almost the exact same thing happened, but for very different reasons. So the Fukushima reactors, so there's 3 of them that underwent partial meltdown, and the primary issue was that they had 2 natural disasters, one after the other, which they were not prepared for. So the earthquake, when it hit in Fukushima, they automatically shut down the reactors, so that system worked fine. So it brought it down to subcritical, and the reactors turned off. So the problem was that there was still all the residual radioactivity in the core that needed to be cooled. Okay, so, and that system, they have an automatic system, emergency system that kicked in, and that worked fine until the tsunami came. So they were in a state where the emergency system was operating properly, and then the tsunami came and basically killed all the pumps that were pumping the water into the reactor core. And so the Fukushima reactors were actually very well designed. They just were not designed to deal with two natural disasters, one after the other. And so when the cooling system failed in Fukushima, because the pumps, the tsunami came in and shut off all the pumps and the power system for the pumps, then basically the the water that was cooling it was evaporated. And so they tried very heroically, of course, to try to bring in water any way they could to try to keep the core cool. But of course, the problem is that is now a very radioactive environment. So when the water evaporates and you start melting down the core, the problem is that stuff that melts gets evaporated, and suddenly you have radioactivity everywhere, and then it's really hard to get people in there. So in Fukushima, they tried very hard to try to get water in without actually sending in people to that they knew would likely die from radiation sickness. And they were partially successful with that, but of course not completely successful. So I don't know what to take out of that, other than nuclear reactors. There are a lot of systems to try to make them safe, but they're of course not foolproof. So they are subject to human errors, like in 3 Mile Island, and they are potentially susceptible to chance coincidences, like 2 natural disasters in a row in Fukushima. So Chernobyl. So Chernobyl in 1986, so a Soviet reactor was not a light water reactor design. It was designed like this pile. So these blocks are graphite, which is carbon, which is a natural moderator. The problem with these designs, and this is what the original nuclear reactors were designed for, is that, well, there's 2 problems. One is they don't have this natural feedback with the water. So if this thing starts to overheat and the cooling water evaporates, then the coolant's gone, but the moderator's not gone. In fact, the water, remember, absorbs some of the neutrons. So in fact, if the water evaporates, the reactions actually grow faster instead of start going away. And so this has exactly the wrong feedback you want for a controlled nuclear reaction. So when the water evaporates, the coolant goes away, but the reaction actually increases. Okay? And the second problem with that is that graphite is flammable. So once it starts heating up, it catches on fire. It burns just like coal. And so Chernobyl was, and a lot of the Russian reactors and Soviet reactors are using this old design, the original design. And I meant to check this. I forget how many of their reactors are still graphite reactors. But I think even they realize that they need to change those over. So Chernobyl, I wish I could say that there was some lesson we learned from that, but the lesson was basically don't let engineers play with your reactor. They were just doing some tests. They turned off all their emergency systems. They heated up the core. It was a really bad human error. They basically were running tests run by engineers who did not know the basics of how reactors run. So huge disaster. Thousands of people affected. Many people lost their lives. And an inherently bad reactor design to start with. 10 minutes. Okay, so reactors. So uranium. So I said in a light water reactor, there are some natural safety features here from the water being both the moderator and the coolant, but it requires us to enrich the uranium. So natural uranium, remember, is only 0.3% uranium-235. Sorry, 0.7%, that's wrong in my notes. Uranium-235. But Uh-huh. Is off. Okay, so Wayne. There we go. Okay, great. Thanks for that, Nathan. Okay, but we've already said in light water reactors we need to get that up to about 3% in order to sustain that reaction, okay, in the light water reactors. So that is called enriched uranium. And the problem is that uranium is not naturally very easily to enrich. Okay? And the reason is because uranium-235 and uranium-238, remember they both come together naturally when we're mining uranium. They are different isotopes, okay, but they're the same element, which means they react identically chemically. Okay? So the normal way we would separate, one element from another inside of some sort of material is we produce a series of chemical reactions that naturally pulls one away from the other. But they react identically chemically, and so you can't do that in order to enrich the uranium. So you have to come up with some way of separating them based on the fact that uranium-238 is just very slightly heavier than uranium-235. Okay? And there are ways to do that, but it's very difficult. Okay? The most common way we do that today is with centrifuges, so these big cylinders that literally just spin the uranium and separate it by the heavier stuff sort of sinking to the bottom. It's like a buoyant force. Okay? But they're not, that mass difference between the nuclei is very, very small, and so that's a very technically difficult process. So that's sort of a natural check on how nuclear technology can spread and propagate, because the process of enriching uranium is naturally just a very difficult thing to do because they are chemically identical. So for a reactor, we have to get up to 3% uranium-235, which is already a challenge. For a weapon, so for if you're producing a nuclear bomb, for it to explode, it has to be highly enriched. Which means greater than 20% uranium-235, which is incredibly challenging to do. That's a very difficult process, okay? And that is what primarily limits the spread of nuclear weapon technology around the world, is producing the enriched uranium. And I mean, your book actually goes into detail on how a uranium-235 bomb is produced. It's not that hard. Okay? The hardest part is getting the uranium to start with. So once you have that enriched uranium, then building the bomb is pretty easy. So getting the uranium enriched is the hard part. Okay, so now one of the other disadvantages of nuclear power is that in any nuclear reactor that is using uranium-235 as fuel and has uranium-238, a natural byproduct of that is plutonium-239. So this is produced in all nuclear reactors. And it's really just a byproduct of neutrons hitting not the uranium-235, but the uranium-238, okay, which is present in the reactors. Okay? And there are a series of reactions, but basically what you're adding is one nucleon into this nucleus and ultimately producing plutonium-239. So this is not a natural isotope. It's one that is produced in nuclear reactors, but it has two really important properties. One is that it is fissionable similar to uranium-235. So it's actually, this means that reactors are actually producing a secondary fissionable fuel. And there are reactor designs called fast breeder reactors, which actually take advantage of that and operate with even higher efficiency than a normal nuclear reactor or a light water reactor. They use both the uranium-235 and the plutonium-239 as fuel. So your book talks about these, and I don't have time to go into detail about them. But I just want to make this point. So I put that range at the beginning, right? How long nuclear fuel could last us. And I said it was 100 to 1,000 years. So that range, is a little bit uncertain, but the lower end is if we're using uranium-235 just as uranium-235, and the higher end is if we're using it and also using the byproducts like plutonium-239 as fuel, okay, in which case we're using it much more efficiently. Okay. Now, the problem is that since this fissions just like uranium-235, that means it can be used not just for nuclear reactors, but for nuclear weapons. And in fact, it's the primary isotope we use in nuclear weapons. And the reason is because it's a different element. So it's very easy to separate in the reactor material. Okay, so the concern is that since it's a different element than uranium, it's very easy to separate chemically. So while it's very hard to make enriched uranium by itself because the uranium-235 and 238 have the same chemical features, okay, if you get these spent fuel rods from a nuclear reactor and they contain the plutonium-239, then it's much easier to pull that out, okay, because it has a very different chemical signature from uranium. Okay? So then when you pull that out, you can potentially use those for fuel, which is good, or it's easy to make it very highly enriched because it's so easy to separate, which means that it's very easy to build up weapons material. So one of the biggest concerns about nuclear technology, even just nuclear reactors spreading around the world, is keeping track of what happens to the fuel after it's been used up, and primarily what's going on with this plutonium-239 in the spent fuel rods, in the used fuel rods, okay? Because that is very easy to produce into a weapon. So this is one of the major concerns, of course, for nuclear energy as well. So let's see, did I answer you guys' questions? Okay, yeah? Any other quick questions? We have 1 more minute. You guys. Okay. I'll see all of you on Tuesday.